السلام عليكم ورحمة الله وبركاته، أسعد الله صباحكم جميعا. اليوم إن شاء الله مكملين معاكم بآخر سؤال من هذا الشابتر وحتى من part thermodynamics. So let's see the question together. طبعا زي ما حكيت هذا السؤال بيجمع كل أفكار الشابترز اللي أخذناهم في part thermodynamics or thermodynamics. So here we start with the substance. So here we have water, okay, contained in a piston cylinder assembly, undergoes two processes, okay, two processes. So we don't know whether it's cycle or not. In series from an initial state. So this is state 1, where the pressure is 10 bar and the temperature is 400 degrees Celsius. So pressure 1, temperature 1 is given. And here is the process 1 to 2. So the water is cooled from state 1. So we have cooling as it's compressed. So here we have V1 greater than V2 at a constant pressure of 10 bar. So V1 equal V2 to saturated vapor state. So here is the phase description of the second state. Okay, so we have this information about second state. We have pressure 2, which is equal to pressure 1, and we have another information that, and they are equal to 10 bar, okay. Or I can refer to this value. And we have another information that state 2 is saturated vapor. So state number 2 is saturated vapor, okay, so sat vapor, saturated vapor. Process 2 to 3, what do we have? The water is cooled, still we are doing cooling at a constant volume, so V2 equal V3, 250 degrees Celsius. So there is no significant change in the flow energy. Sketch both processes on TV. I will add also VB. Okay. For the overall process, determine the work from process 1 to 2, work from process 2 to 3, the net work. For overall process, determine the heat transfer. So we need also to find the Q1, Q2, Q2 to 3. Okay, let's move to the solving board and try to solve this problem. Let's start with writing down the table, okay, mapping table. So here we have state 1 or state number. Here we have pressure in kilopascal. Okay, and here we have temperature, degrees Celsius, and here we have phase description. So here is state 1, state 2, and state 3. Okay, so in the statement of this problem, it's mentioned that pressure 1 equal to 10 bar. So 10 bar, if I need to convert it, I'll refresh. So bar equal, or pressure equal, pressure 1, 10 bar, or I need to convert it to kilopascal. So every 1 bar gives 10 to the power 5 or 10 to the power 2 kilopascal. Because I need it in kilopascal. If it's in pascal, then this is 10 to the power 5. This is equal 1000 kilopascal. Okay. Let me go back up and write down that we have here 1,000, and pressure 2 again it is 1,000. Okay. Pressure 3 is unknown. The water cooled 250. So there is no information about the pressure. Okay, so what else we have? We have temperature 400. Here we don't know any information about the phase in state 1. In state 2, uh, there is no information about temperature, neither the volume, but we have compressed. Okay, and this is saturated vapor. Saturated vapor means x equal to 1. Okay. Okay. In state number 3, it happens at a constant volume. So this is 150. And V1 equal to V2. Maybe it's better to add a column, special column for volume. Okay. So here there is no information about volume, but we have compression. Here constant V2 equal V3. And here this. Okay, so this is all information that we have. So let's start finding out the unknowns first. Then we'll come back to the first requirement, which is drawing the BVTV diagram. Okay. Let's start with the state 1. State number 1. So what do we have? We have pressure 1 equal to 1,000 kilopascal, and we have temperature 1 equal to 400 degrees Celsius. What is the first step? The first step is going to thermodynamic tables. So here is the thermodynamic tables, and I'll go to water table, saturated water table, and I'll start with the pressure table. Okay, so we are looking for table A5. So here it is. We need pressure of 1,000. So in the first table it's not there. The second table, saturated water pressure table, we need this value, 1,000. So here is the Tsat. Tsat is 179.88. So Tsat is 179.88, and our value is bigger than Tsat. So that means go to superheated table. Okay, once T1 is less than or greater than Tsat, that means we need to benefit from such a superheated table. So I write down the values. So here we have V1. So let me go to the table, superheated table. So I need 1,000, which is 1 mega. Okay, here is the superheated, and here is the corresponding pressure. I look for temperature of 400. Okay, here is the values. So here is the volume, which is 0.3066.1. Okay, let me write them on the solving board. So in the solving board, I'll go down. So V1 will equal to, let me use another color. So V1 is 0.3066.1 meter cube per kilogram. As well, we need U1. So U1 equal to 2957.9 kilojoule per kilogram. Here units is very important. Okay, so this is state 1. Now we need also state 2. So in state 2, what do we have? State. So state number 2. In state number 2, we have the following information. We have pressure constant. So V2 equal V1, and it's equal to 1000 kilopascal. And we have X2 equal to saturated vapor, which is 1 exactly on the intersection. So the values that we are that we need is V2 must be equal to Vg. Okay, and the same for U. U2 must equal Ug. Okay, so let me go back to the table. Here is the table. So I go back to the saturated water pressure table, and I need 1000. Here is the value. So the volume that we need is 0.19436, and Ug is 2582. Okay, so here I write down Vg equal to 0.19, sorry, 436 course meter cube per kilogram, and Ug equal to 258, 2.8 kilojoule per kilogram. Okay, so now we need to find the third state. What do we have for the third state? State number. On state number 3, we have the following information. We have V2. So this process is cooling, but at a constant volume. So V3 equal V2, and it's equal to 0.19436 meter cube per kilogram. Okay, and the corresponding temperature is 150. So T3 equal 150 degrees Celsius. So what to do? We'll go to the temperature table, saturated temperature table, and we'll compare our value T3, which is 0.19436, with Vf and Vg. So if this relation, we'll ask ourselves, is this value between Vf and Vg from those tables? So let me go back to the saturated water, but temperature, because we have temperature in set 3. So going back to temperature table, here is the temperature table, and we need 400 degrees Celsius. Okay, so here is Vf and here is Vg. So they are third and fourth column. So 400, or it is 150. Yeah, it is 150. So let me go up. So here is 150, and third and fourth column represent Vf and Vg. So here is our value, 0.001091 and 0.39248. Let me take them to the solving board. So Vf 0.00191 and Vg is 0.39248. So is our value between these two values, so 0.19 greater than 0.001 and it's less than 0.03, so yes, this is correct. So once it is correct, that means we can go and find out the corresponding x. So the meaning that this relation is correct, that means what is the phase here? It is saturated mixture, correct? So in the table we must fill that the phase of this shape is saturated mixture. This is why we need to find x3 in order to find u3. So x3, the equation is v minus vf divided by vfg. Okay, so this is equal to 0.19436 minus 0.001091 divided by 0.39248 minus 0.001091. So if I use my calculator, 0.19436 minus 0.001091 divided by 0.39248 minus 0.001091. So the quantity here is equal to, so x3 equal to 0.4938, okay, which is equal to almost 0.5, but we don't do this, okay, don't do an approximation. Okay, now we need to find u3. So from this equation, u3 equal to uf plus x3 multiplied by ufg. Uf from where? From the same table. Okay, where is u? Columns. The fifth up to seventh column. Okay, here is the value. So here we have 631 as uf, and this one is 2559 as ug, or we can take the ufg, which is the subtraction of ug minus uf. Okay, so let me write them down. So we have 631.66 plus 0.493 multiplied by ufg, which is 192.7.4. I'll use my calculator. 1927.4 multiplied by 493 plus 631.6. So the answer is 1583.4 kilojoule per kilo. So this is U3. Okay. Now what we'll do, we'll try to answer after we find out all information. We'll try to answer the requirements. So in the first part, we need to draw TV, and here is the dome. Okay. Yeah, and here is the dome. Here is the pressure line, which is constant. P is constant. And here is the VV diagram. And here is the temperature is constant. So let me start with the TV diagram and start with the first process. First process we have, let me change the color. We have the water is cooled as it's compressed. So V1 we said earlier greater than V2, and the pressure is constant. So we are starting from superheated as we discover, and we'll transfer to state 1 at a constant pressure. So here is state 2, and we find out that state 2 is saturated vapor. Now state 3 happens at a constant volume, and state 3 is located in the mixture region. Here is the mixture region, and V1 is constant. Okay, the same processes we can draw it on BV diagram. On a BV diagram, it's mentioned that pressure is constant as it's cooled down. So here is state 1 in the superheated. We transfer to state 2 until we reach saturated vapor at a constant pressure, this process, and it's cooling down. Okay, so if I want to draw another temperature line, as we go higher, the temperature will be higher. Okay, so yes, it's cooling down. Now from state 2, we'll go straight down because this process happens at a constant volume, and we reach to mixture region. So this is the answer for the first part. Now the second part, in the second part, we need to find W net, which is equal to W12 plus W2 to 3. Now W2 to 3 constant volume means this is equal to 0, but state or process 1 to 2, this process at a constant pressure, so this is pressure multiplied by V2 minus V1. Okay, so this is equal pressure, which is 1000 kilopascal, multiplied by V2 equal to 0.19436 minus V1, which is 0.30661. So using my calculator, the answer would be negative, correct? So 0.19436 minus 0.30661 multiplied by 1000. So the answer is, since this is a compression, then we expect that the sign is minus 0.25, and unit is kilojoule per kilogram, and he asked to find this value in kilojoule per kilogram. If we have mass, then we'll multiply by mass to find the unit in kilojoule. Now the The second requirement is to find QC. Find the Q, the total Q. So Q total or Q net, again it's equal to Q1 to 2 plus Q2 to 3. Now Q1 to 2, I apply the first law, which is equal Q1 to 2 minus work 1 to 2 equal delta U. I write in specific. So Q1 to 2 equal delta U plus work 1 to 2, and this is equal to delta U means U2 minus U1, and U2 it was 1583.9 minus, you can go back and check this value, 2957.9. Okay, this is U1 and this is U2. So if I go back to show you these values, let's go back. So yes, so let me go down. So here is U1, okay, and where is U2? So here is U2. So I think I substitute U3 instead of U2. Let me go and check. Yes, I substitute U3 instead of U2. So let me erase this one. So we need to write 2582.9 plus minus 112.25. Okay, and the answer is, so 2582.9 minus 2957.5 minus 112.25, and the answer is minus 486.85 kilojoule per kilogram. Now we'll do the same with Q 2 to 3 minus W 2 to 3 equal to delta. Where 2 to 3, we said earlier that this is equal to 0, and delta U means U3 minus U2. Okay, so Q2 to 3 equal to 1583.9 minus 258, and the answer is 0.9 minus 25. So the answer is equal to minus 998.9 kilojoule per kilogram. So the net or the Q total or Q net equal to Q, which is minus Q1 to 2 minus 486.8, so minus 486.85 minus 998.9, and the answer is minus 1485.75 here. And the minus sign means Q lost it to the surrounding. Okay, so that's all for this problem. Okay, so you could notice here that we benefit from the equation of the work based on the type of the process, and we benefit from the first law of thermodynamics, and then we benefit from the thermodynamic tables. Okay, so the question, if I bring uh, question on this chapter, I'll bring it look like this one. Okay. So that's it for thermodynamic part. Let me move to heat transfer part. So here is the heat transfer part. Okay, and let me activate the pen. So heat transfer part. So the most important thing that we are going to do in this part is to demonstrate and explain the terminology behind heat transfer and classify the types of how heat is transferring from one medium to another. So we must understand the heat transfer and then explain the conduction, convection, and radiation terminology. So heat transfer, heat always moves from a warmer place to a cooler place. And this is the natural thing of transferring heat. So usually heat transfer from higher temperature, more energetic particles to lower temperature or cooler place or less energetic particles. Okay. Hot objects like coffee, for example, in a cooler room, what will happen to it? Will cool to room temperature. Okay, this is the natural thing. So the cup, for example, will lose its temperature until it reach the room temperature, and it will stop heat. It will stop heat transfer. Okay, while the cold objects in a warmer room, okay, or we can say in the same room, will heat up to room temperature. Okay, it will heat up, or the temperature or the heat in this room will transfer to the cold object. As a result, cold object will gain heat. Okay, will heat up. Okay. Question: if we have a cup of coffee means we have the high. Okay, its temperature is very high, and a red popsicle or ice cream were left on the table in this room, in your room. Okay, imagine every one of you that you have cup of coffee and ice cream on his table. What would happen to them, to the cup of coffee and to the ice cream, and why? So, as you expect that you are living in a room where the temperature is around 25, 24, something like this. So if the room temperature is 24, which is less than the temperature of the cup of coffee, okay, and it is higher than the temperature of the popsicle, okay, the ice cream, what will happen? What will happen to the cup of coffee? The cup of coffee, because we have temperature difference, okay, the heat will transfer from higher to the room until the cup of coffee reach to the room temperature. And what will happen to the ice cream? The ice cream will cool down by gaining heat from the room until it melts down because it exists in a solid phase. It is ice, okay? So it is in solid phase. So it will start gain heat until it melts. Once it melts, the liquid resulted is cool. This liquid will again gain heat until it warm. Okay, so this is the answer. Why? Because there is temperature difference. The cup of coffee will cool. Okay, it will lose temperature, so it will cool down until it reach the room temperature. This is what will happen to the cup of coffee. Why? Because we have temperature difference. Whereas the popsicle will melt, and then the liquid will warm to room temperature. Okay, so it will transfer its phase from solid to liquid, and then this liquid, which exists at lower pressure than the room temperature, it will cool down, or sorry, it will warm up until it reaches to the room temperature. Heat transfer methods or types. The heat transfer in three ways. Either it transfer by conduction or convection, okay, or convection, sorry, or radiation. This is the third type. And here is very good example of transferring heat. So if we have cooking pan, okay, so here we have heat source, okay, here it is, and here we have the cooking pan, okay. So you can notice that here we have metal, okay, and here we have certain thickness of this metal, okay, here in the surrounding. First the slide, okay, we have metal. Then inside we have water, which is boiled, okay. So you can now notice that in this medium, heat transferred through conduction, and in this medium we have heat transferred through convection, and here we have heat transferred due to radiation. So how we can define each scenario? Okay, I'll start with the conduction and try to notice what happens to the molecules here. So here we have a sheet metal, okay, and this sheet metal we have a source of heat in the side. So what happens to this sheet metal? The heat will transfer from this side until it reaches the other side. Okay, so imagine that this is a sheet metal. Okay, this is a sheet metal, and heat transfer throughout this sheet metal. So when you heat a metal strip at one end, the heat travels to the other end. But why? So the heat here, we said the heat here conducted. Then we call it conduction. Okay? What happens is conduction. But how? The heat is conducted to the other side. But how heat conducted? As you heat the metal, the particles, as you can see, vibrate in its place, because whenever we have solid, we said earlier that the molecules of the solid have very strong bonding. Okay, so it's vibrate in its place. These vibration make the adjacent particles vibrate due to very strong bonding. Okay, the other molecules will vibrate, so we have kinetic energy of the molecules. Okay, as it starts vibrate, its temperature will start to increase. and so on. So this vibrate, the adjacent one also vibrate, and the vibration transferring throughout the metal sheet. So this vibration are passed along the metal, and so is the heat. So the movement is transferring, or the vibration is transferring as well as the heat. So this is the reason why heat is transferring through a solid. Okay, whenever we have heat transfer through a solid, we call it conduction. But why this happens? Why heat transfer through a solid? By having this property, the vibration of the bond of the molecules. Another reason why heat is transferring through solid, if we have metal, then we'll have this characteristic. The outer electrons of the metal atom drift and are free to move throughout the metal. So when the metal is heated, this drifted atoms from each this drifted electron, from each atom will form a sea of electrons. Okay, every atom have one electron drifted. Okay, then we have sea of electrons from all the atoms of the solid object. So when the metal is heated, this sea of electrons gain kinetic energy and transfer it throughout the metal. So we have now two reasons why heat is transferred in the solid objects, especially if we are talking about metals. So we have vibration of the molecules, and we have sea of electrons, which are drifted, okay, and they are free to move. So they are move and they transferring heat as well. But in the insulators, العوازل, such as wood and plastics, do not have this sea of electrons. So heat transferring through wood and plastic due to vibration of the molecules. So we only have one source of heat transfer, okay, which is vibration. It is conduction, but conduction happens due to vibration and sea of electrons. In insulators, we have only vibration. Which is why the plastics and wood, they do not conduct heat as well as the metals. At the end, we classify them as insulators. Okay. So if you are heating up metal and wood, the heat will not be conducted at the same rate. Yes, after a while, the wood object, if we are heating this side of a wood object, the heat will be transferred to the other side, but it will take certain time. Okay, but if we have metal, the heat transfer is instant. So let us ask this question. Why does metal feel colder than wood? So here we have same shape, same weight, okay? And you catch in one hand the wood object, and in the other hand you catch you hold the wood metal object. So whenever you catch both of them, each one of them in one hand, you feel that the metal is colder than the wood, but they are at the same temperature. So here, let us say that here we have 5 degrees Celsius, and here we have this one is 5 degrees Celsius. Same shape, same everything, but you feel that the metal is colder than the wood. Why? Why this happens? So you can stop the video and think why this is happening. Okay, the answer is metal is conductor, as we demonstrated earlier in the previous slide, and wood is insulator. Metal conducts heat away from your hand faster. Okay, wood does not conduct heat away from your hands as well as the metal. So that the wood feels warmer than the metal. Okay, So this is what happens. So your hand is around 36 degrees Celsius, which is higher. So heat transfer from higher temperature to the lower temperature. In the scenario of metal, so heat here will transfer faster through conduction. Okay, because metal classified as conductor. While here your hand around 36 and here 5, heat will transfer but very slower than the metal. Okay. Convection, I'll start talking about this topic in the coming lecture. Okay, so I'll stop up to here. Okay, and I'll start this this topic next lecture, inshallah. Stay safe and see you soon.